Students' learning outcomes. After studying this unit, the students will be able to define momentum, force, inertia, friction, and centripetal force. Solve problems using the equation force equals change in momentum, change in time. Explain the concept of force by practical examples of daily life. State Newton's laws of motion. Distinguish between mass and weight and solve problems using F equals ma and W equals milligram. Calculate tension and acceleration in a string during motion of bodies connected by the string and passing over frictionless pulley using second law of motion. State the law of conservation of momentum. Use the principle of conservation of momentum in the collision of two objects. Determine the velocity after collision of two objects using the law of conservation of momentum. Explain the effect of friction on the motion of a vehicle in the context of tire surface, road conditions including skidding, braking force. Demonstrate that rolling friction is much lesser than sliding friction. List various methods to reduce friction. Conceptual linkage. This unit is built on Force and Motion, Science IV. This unit leads to Motion and Force, Physics XI. Physics 958 Unit 3, Dynamics. Explain that motion in a curved path is due to a perpendicular force on a body that changes direction of motion but not speed. Calculate centripetal force on a body moving in a two-circle using MV/R. State what will happen to you while you are sitting inside a bus when the bus I starts moving suddenly, 2 stops moving suddenly, 3 turns a corner to the left suddenly. Write a story about what may happen to you when you dream that all friction suddenly disappeared. Why did your dream turn into a nightmare? The students will be able to identify the relationship between load and friction by sliding a trolley carrying different loads with the help of a spring balance on different surfaces. The students will be able to identify the principle of dynamics with reference to the motion of human beings, objects, and vehicles, e.g. analyze the throwing of a ball, swimming, boating and rocket motion. Identify the safety devices, such as packaging of fragile objects, the action of crumple zones and seatbelts, utilized to reduce the effects of changing momentum. Describe advantages and disadvantages of friction in real-world situations, as well as methods used to increase or reduce friction in these situations, e.g. advantages of friction on the surface of car tires, tire tread, cycling parachute, knots in string, disadvantages of friction, and methods for reducing friction. Investigation skills. Science, technology and society connection. Major concepts. 3.1 Momentum. 3.2 Newton's laws of motion. 3.3 Friction. 3.4 Uniform circular motion. Figure 3.1, the food vendor on move. Physics 958 Unit 3, Dynamics. Between moving parts of industrial machines and on wheels spinning on axles. Identify the use of centripetal force in I. Safe driving by banking roads, 2. Washing machine dryer, 3. Cream separator. In kinematics, we have studied the changes in motion only. Our understanding about the changes in motion is of little value without knowing its causes. The branch of mechanics that deals with the study of motion of an object and the cause of its motion is called dynamics. In this unit, we shall study momentum and investigate what causes a change in the motion of a body and what role the mass of a body plays in its motion. This inquiry leads us to the concept of force. We shall also study the laws of motion and their applications. 3.1 Force, inertia, and momentum. Newton's laws of motion are of fundamental importance in understanding the causes of motion of a body. Before we discuss these laws, it is appropriate to understand various terms such as force, inertia, and momentum. Force. We can open a door either by pushing or pulling it. Figure 3.1 shows a man pushing a cart. The push may move the cart or change the direction of its motion or may stop the moving cart. A batsman in figure 3.2 is changing the direction of a moving ball by pushing it with his bat. A force may not always cause a body to move. Look at the picture shown in figure 3.3. A boy is pushing a wall and is thus trying to move it. Could he move the wall? A goalkeeper needs a force to stop a ball coming to him as shown in figure 3.4. Thus, we understand that. Figure 3.2, ball is turned into different direction as it is pushed by the batsman. Figure 3.3, a boy is pushing the wall. Figure 3.4, goalkeeper is stopping the ball. Physics 958 Unit 3, Dynamics. A force moves or tends to move, stops or tends to stop the motion of a body. The force can also change the direction of motion of a body. What happens when you press a balloon? You can cut an apple with a knife by pushing its sharp edge into the apple. Thus a force can also change the shape or size of a body on which it acts. Inertia. Galileo observed that it is easy to move or to stop light objects than heavier ones. Heavier objects are difficult to move, or if moving then difficult to stop. Newton concluded that everybody resists to the change in its state of rest or of uniform motion in a straight line. He called this property of matter as inertia. He related the inertia of a body with its mass, greater is the mass of a body, greater is its inertia. Inertia of a body is its property due to which it resists any change in its state of rest or motion. Let us perform an experiment to understand inertia. Experiment 3.1. Take a glass and cover it with a piece of cardboard. Place a coin on the cardboard as shown in figure 3.5. Now flick the card horizontally with a jerk of your finger. Does the coin move with the cardboard? The coin does not move with the cardboard due to inertia. Where does the coin go as the cardboard flies away? Consider another example of inertia. Cut a strip of paper. Place it on the table. Stack a few coins at its one end as shown in figure 3.6. Pull out the paper strip under the coins with a jerk. Do you succeed in pulling out the paper strip under the stacked coins without letting them to fall? Why do the coins remain stacked on pulling out the paper strip quickly under the stack? Figure 3.5, the coin fails into the glass as the card flicks away. Figure 3.6, coins stacked over remain undisturbed on pulling the paper strip quickly. Physics 959 Unit 3, Dynamics. Momentum. A bullet has a very small inertia due to its small mass. But why does its impact is so strong when it is fired from the gun? On the other hand, the impact of a loaded truck on a body coming its way is very large even if the truck is moving slowly. To explain such situation, we define a new physical quantity called momentum. Momentum of a body is the quantity of motion it possesses due to its mass and velocity. The momentum p of a body is given by the product of its mass m and velocity v. Thus, p equals mv. 3.1. Momentum is a vector quantity. Its SI unit is -1 kg/s. 3.2 Newton's laws of motion. Newton was the first to formulate the laws of motion known as Newton's laws of motion. Newton's first law of motion. First law of motion deals with bodies which are either at rest or moving with uniform speed in a straight line. According to Newton's first law of motion, a body at rest remains at rest provided no net force acts on it. This part of the law is true as we observe that objects do not move by themselves unless someone moves them. For Example, a book lying on a table remains at rest as long as no net force acts on it. Similarly, a moving object does not stop moving by itself. A ball rolled on a rough ground stops earlier than that rolled on a smooth ground. It is because rough surfaces offer greater friction. If there would be no force to oppose the motion of a body, then the moving body would never stop. Thus Newton's first law of motion states that a body continues its state of rest or of uniform motion in a straight line provided no net force acts on it. Net force is the resultant of all the forces acting on a body. And since Newton's first law of motion deals with the inertial property of matter, therefore, Newton's first law of motion is also known as law of inertia. We have observed that the passengers standing in a bus fall forward when its driver applies brakes suddenly. It is because the upper parts of their bodies tend to continue their motion, while lower parts of their bodies in contact with the bus stop with it. Hence, they fall forward. Newton's second law of motion. Newton's second law of motion deals with situations when a net force is acting on a body. It states that when a net force acts on a body, it produces acceleration in the body in the direction of the net force. The magnitude of this acceleration is directly proportional to the net force acting on the body and inversely proportional to its mass. If a force produces an acceleration in a body of mass m, then we can state mathematically that, putting k as proportionality constant, we get, in SI units, the value of k comes out to be 1. Thus equation 3.2 becomes, SI unit of force is Newton, N. According to Newton's second law of motion, 1 Newton, 1 N, is the force that produces an 2 acceleration of 1 millisecond in a body of mass of 1 kilogram. Thus, a force of 1 Newton can be expressed as, when a bus takes a sharp turn, passengers fall in the outward direction. It is due to inertia that they want to continue their motion in a straight line and thus fall outwards. Do you know? Physics 960 Unit 3, Dynamics. Here, using the formula. Example 3.1. Find the acceleration that is produced by a 20 N force in a mass of 8 kilograms. Solution. -2. Thus acceleration produced by the force is 2.5 milliseconds. Example 3.2. A force acting on a body of mass 5 kilograms produces an acceleration of 10 milliseconds. What acceleration the same force will produce in a body of mass 8 kilograms? Solution. Here, applying Newton's second law of motion, we get, comparing the equations, we get, or Physics 961 Unit 3, Dynamics. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. N10. Block. 1 Newton. Spring balance. -2. Hence, the acceleration produced is 6.25 milliseconds. Example 3.3. A cyclist of mass 40 kilograms exerts a force of 200 N to move -2 his bicycle with an acceleration of 3 milliseconds. How much is the force of friction between the road and the tires? Solution. Thus, the force of friction between the road and the tires is 80 N. Mass and weight. Generally, mass and weight are considered similar quantities, but it is not correct. They are two different quantities. Mass of a body is the quantity of matter possessed by the body. It is a scalar quantity and does not change with change of place. It is measured by comparison with standard masses using a beam balance. On the other hand, weight of a body is the force equal to the force with which Earth attracts it. It varies depending upon the value of g, acceleration due to. Here, net force. Force of friction as net force. Net force equals applied force, force of friction. Hence, Figure 3.7, spring balance is used to measure the force or weight of a body. Physics 962 Unit 3, Dynamics. W. Gravity. Weight y a body of mass m is related by the equation W equals milligram. 3.5, weight is a force and thus it is a vector quantity. Its SI unit is Newton, N, the same as force. Weight is measured by a spring balance. Newton's third law of motion deals with the reaction of a body when a force acts on it. Let a body exerts a force on another body B. The body B reacts against this force and exerts a force on body A. The force exerted by body A on B is the action force, whereas the force exerted by body B on A is called the reaction force. Newton's third law of motion states that, to every action there is always an equal but opposite reaction. According to this law, action is always accompanied by a reaction force and the two forces must always be equal and opposite. Note that action and reaction forces act on different bodies. Consider a book lying on a table as shown in Figure 3.8. The weight of the book is acting on the table in the downward direction. This is the action. The reaction of the table acts on the book in the upward direction. Consider another example. Take an air-filled balloon as shown in Figure 3.9. When the balloon is set free, the air inside it rushes out and the balloon moves forward. In this example, the action is by the balloon that pushes the air out of it when set free. The reaction of the air which escapes out from the balloon acts on the balloon. It is due to this reaction of the escaping air that moves the balloon forward. A rocket such as shown in Figure 3.10 moves on the same principle. When its fuel burns, hot gases escape out from its tail with a very high speed. The Figure 3.10, a rocket taking off. Figure 3.9, reaction of the air pushed out of the balloon moves it. Figure 3.8, action of the book and reaction on it. Physics 963 Unit 3, Dynamics. Physics 964 Unit 3, Dynamics. Reaction of these gases on the rocket causes it to move opposite to the gases rushing out of its tail. Tension and acceleration in a string. Consider a block supported by a string. The upper end of the string is fixed on a stand as shown in Figure 3.11. Let W be the weight of the block. The block pulls the string downwards by its weight. This causes a tension T in the string. The tension T in the string is acting upwards at the block. As the block is at rest, therefore, the weight of the block acting downwards must be balanced by the upwards tension T in the string. Thus the tension T in the string must be equal and opposite to the weight W of the block. Vertical motion of two bodies attached to the ends of a string that passes over a frictionless pulley. Consider two bodies A and B of masses m1 and m2 respectively. Let m is greater than m. The bodies are 1-2 attached to the opposite ends of an inextensible string. The string passes over a frictionless pulley as shown in Figure 3.12. The body A being heavier must be moving downwards with some acceleration. Let this acceleration be A. At the same time, the body B attached to the other end of the string moves up with the same acceleration A. As the pulley is frictionless, hence tension will be the same throughout the string. Let the tension in the string be T. Since the body A moves downwards, hence its weight mg is greater than the tension T in the string. One net force acting on body A equals mg1, T. W W W A BT MG2 A T MG1. Figure 3.11. Weight of the block pulls the string downwards. Figure 3.12. Bodies attached to the ends of a string that passes over a frictionless pulley. Physics 965 Unit 3. Dynamics. According to Newton's second law of motion, as body B moves upwards, hence its weight mg2 is less than the tension T in the string. Net force acting on body B equals T mg2 according to Newton's second law of motion. Net force acting on body B equals T mg2 according to Newton's second law of motion. Net force acting on body B equals T mg2 according to Newton's second law of motion. Adding equation 3.6 and equation 3.7, we get acceleration A. Divide equation 3.7 by equation 3.6 to find tension T in the string. The above arrangement is also known as Atwood machine. It can be used to find the acceleration g due to gravity using EQ 3.8. Example 3.4. Two masses 5.2 kilograms and 4.8 kilograms are attached to the ends of an inextensible string which passes over a frictionless pulley. Find the acceleration in the system and the tension in the string when both the masses are moving vertically. Solution: do you know? An Atwood machine is an arrangement of two objects of unequal masses such as shown in figure 3.12. Both the objects are attached to the ends of a string. The string passes over a frictionless pulley. This arrangement is sometimes used to find the acceleration due to gravity. A -2. Thus the acceleration in the system is 0.4 milliseconds and tension in the string is 50 N. Motion of two bodies attached to the ends of a string that passes over a frictionless pulley such that one body moves vertically and the other moves on a smooth horizontal surface. Consider two bodies A and B of masses m and 1m respectively attached to the ends of an inextensible two-string as shown in figure 3.13. Let the body A moves downwards with an acceleration A. Since the string is inextensible, therefore, body B also moves over the horizontal surface with the same acceleration A. As the pulley is frictionless, hence tension T will be the same throughout the string. Since body A moves downwards, therefore, its weight mg is greater than the tension T in the string. One net force acting on body A equals mg1 T. According to Newton's second law of motion, the forces acting on body B are I. Weight mg of the body B acting downward. 2. Reaction R of the horizontal surface acting on body B in the upwards direction. 3. Tension T in the string pulling the body B horizontally over the smooth surface. As body B has no vertical motion, hence resultant of vertical forces, mg and r, must be 0. 2. Thus, the net force acting on body B is T. According to Newton's second law of motion. Physics 966 Unit 3, Dynamics. B R mg2 mg1 A T A A. Figure 3.13, motion of mass is attached to a string that passes over a frictionless pulley. Physics 967 Unit 3, Dynamics. Adding x 3.10 and 3.11, we get acceleration as. Putting the value of A in equations 3.11 to get tension T as. Example 3.5. Two masses 4 kilograms and 6 kilograms are attached to the ends of an inextensible string which passes over a frictionless pulley such that mass 6 kilograms is moving over a frictionless horizontal surface and the mass 4 kilograms is moving vertically downwards. Find the acceleration in the system and the tension in the string. Solution. 2. Thus the acceleration in the system is 4 milliseconds and tension in the string is 24 N. Force and the momentum. Consider a body of mass m moving with initial velocity v. Let a force F acts on the body which I produces an acceleration in it. This changes the velocity of the body. Let its final velocity after time becomes Vf. If pi and pf be the initial momentum and final momentum of the body related to initial and final velocities respectively, then thus the rate of change in momentum is given by since is the rate of change of velocity equal to the acceleration produced by the force F. According to Newton's second law of motion. Equation 3.14 also defines force and states Newton's second law of motion as when a force acts on a body, it produces an acceleration in the body and will be equal to the rate of change of momentum of the body. SI unit of momentum defined by equation 3.14 is 1 Newton second, ns, which is the same as kgms. Example 3.6. A body of mass 5 kilograms is moving with a velocity of -110 milliseconds. Find the force required to stop it in 2 seconds. Solution. And change in equals final initial momentum. During an accident, crumple zones collapse. This increases the impact time by providing extra time for crumpling. The impact of force is highly reduced and saves the passengers from severe injuries. In an accident high speed, the impact force is very large due to the extremely short stopping time. For safety purposes, vehicles have rigid cages for passengers with crumple zones at their front and rear ends. Useful information. Useful information. Air enclosed in the cavities of these materials makes them flexible and soft. During any mishap, they increase the impact time on fragile objects. An increase in impact time lowers the rate of change of momentum and hence lessens the impact of force. This lowers the possible damage due to an accident. Fragile objects such as glasswares etc. are packed with suitable materials such as styrofoam rings, balls, polythene sheets with air sacs etc. Physics 968 Unit 3, Dynamics. Before collision. After collision. At collision. U1 U2 M1 M2 M1 M2 V1 V2 M2 M1. Physics 969 Unit 3, Dynamics. Useful information. In case of an accident, a person not wearing seatbelt will continue moving until stopped suddenly by something before him. This something may be a windscreen, another passenger or back of the seat in front of him, her. Seatbelts are useful in 2 ways. They provide an external force to a person wearing seatbelt. The additional time is required for stretching seatbelts. This prolongs the stopping time for momentum to change and reduces the effect of collision. Figure 3.14, collision of two bodies of spherical shapes. Thus 25 N force is required to stop the body. Law of conservation of momentum. Momentum of a system depends on its mass and velocity. A system is a group of bodies within certain boundaries. An isolated system is a group of interacting bodies on which no external force is acting. If no unbalanced or net force acts on a system, then according to equation 3.14 its momentum remains constant. Thus the momentum of an isolated system is always conserved. This is the law of conservation of momentum. It states that the momentum of an isolated system of two or more than two interacting bodies remains constant. Consider the example of an air-filled balloon as described under the third law of motion. In this case, balloon and the air inside it form a system. Before releasing the balloon, the system was at rest and hence the initial momentum of the system was zero. As soon as the balloon is set free, air escapes out of it with some velocity. The air coming out of it possesses momentum. To conserve momentum, the balloon moves in a direction opposite to that of air rushing out. Consider an isolated system of two spheres of masses m and m as shown in figure 3.14. They are 1, 2 moving in a straight line with initial velocities u1 and u2. Physics 970 Unit 3, Dynamics. Respectively, such that u is greater than u. Sphere of mass 1, 2 m approaches the sphere of mass m as they move. 1, 2 initial momentum of mass m equals m u initial momentum 1, 1, 1 of mass m equals m u total initial momentum of 2, 2, 2 the system before collision equals m u plus mu. 3.15, 1, 1, 2, 2 after some time mass m hits m with some force. 1, 2 according to Newton's third law of motion, m exerts an 2 equal and opposite reaction force on m. Let their velocities 1 become v1, 2 and v respectively after collision. Then final momentum of mass m equals mv, final 1, 1, 1 momentum of mass m 2, 2, 2 equals mv. According to the law of conservation of momentum. Equation 3.17 shows that the momentum of an isolated system before and after collisions remains the same, which is the law of conservation of momentum. Law of conservation of momentum is an important law and has vast applications. Consider a system of gun and a bullet. Before firing the gun, both the gun and bullet are at rest, so the total momentum of the system is zero. As the gun is fired, bullet shoots out of the gun and acquires momentum. To conserve momentum of the system, the gun recoils. According to the law of conservation of momentum, the total momentum of the gun and the bullet will also be zero after the gun is fired. Let m be the mass of the bullet and v be its velocity on firing the gun, m be the mass of the gun and v be the velocity. Total initial momentum of the system before collision, total final momentum the system after collision. Equals total final momentum of the system after collision equals mv plus mv. 3.16, 1122 equals Physics 971 Unit 3, Dynamics. Equation 3.19 gives the velocity backslash of the gun. Negative sign indicates that velocity of the gun is opposite to the velocity of the bullet, i.e., the gun recoils. Since mass of the gun is much larger than the bullet, therefore, the recoil is much smaller than the velocity of the bullet. Rockets and jet engines also work on the same principle. In these machines, hot gas is produced by burning of fuel rush out with large momentum. The machines gain an equal and opposite momentum. This enables them to move with very high velocities. Example 3.7 A bullet of mass 20 g is fired from a gun with a 1 muzzle velocity 100 milliseconds. Find the recoil of the gun if its mass is 5 kilograms. Solution. With which it recoils. Thus the total momentum of the gun and the bullet after the gun is fired will be, according to the law of conservation of momentum, total momentum of the gun and the bullet after the gun is fired. Total momentum of the gun and the bullet after the gun is fired. Total momentum of the gun and the bullet before the gun is fired. Or, hence, according to the law of conservation of momentum. Putting the values, we get. The negative sign indicates that the gun recoils, i.e., moves in the backward direction opposite to the motion of 1. The bullet with a velocity of 0.4 milliseconds. 3.3 Friction. Have you noticed why a moving ball stops? Why? Bicycle stops when the cyclist stops pedaling? Naturally, there must be some force that stops moving objects, since a force not only moves an object, but also stops moving object. The force that opposes the motion of moving objects is called friction. Friction is a force that comes into action as soon as a body is pushed or pulled over a surface. In case of solids, the force of friction between two bodies depends upon many factors such as nature of the two surfaces in contact and the pressing force between them. Rub your palm over different surfaces such as table, carpet, polished marble, surface, brick, etc. You will find smoother is the surface, easier it is to move over the surface. Moreover, harder you press your palm over the surface, more difficult would it be to move. Why friction opposes motion? No surface is perfectly smooth. A surface that appears smooth has pits and bumps that can be seen under a microscope. Figure 3.17 shows two wooden blocks with their polished surfaces in contact. A magnified view of two smooth surfaces in contact shows the gaps and Figure 3.15, a cyclist keeps on pedaling to overcome friction. Figure 3.16, to walk or to run friction is needed to push the ground backward. Physics 972 Unit 3, Dynamics. Cold welds. Contacts between them. The contact points between the two surfaces form a sort of cold welds. These cold welds resist the surfaces from sliding over each other. Adding weight over the upper block increases the force pressing the surfaces together and hence increases the resistance. Thus, greater is the pressing force, greater will be the friction between the sliding surfaces. Friction is equal to the applied force that tends to move a body at rest. It increases with the applied force. Friction can be increased to certain maximum value. It does not increase beyond this. The maximum value of friction is known as the force of limiting friction, F. It depends on the normal reaction, pressing force, between the two surfaces in contact. The ratio between the force of limiting friction F and the normal reaction R is constant. This constant is called the coefficient of friction and is represented by friction is needed to walk on the ground. It is risky to run on wet floor with shoes that have smooth soles. Athletes use special shoes that have extraordinary ground grip. Such shoes prevent them from slipping while running fast. What will we do to stop our bicycle? We will apply brakes. The rubber pads. Figure 3.17, a magnified view of the two surfaces in contact. Tidbits. Pushing the opposite walls by palms and feet increases friction. This enables the boy to move up on the walls. Coefficient of friction between some common materials. Thus, or if m be the mass of the block, then for horizontal surface. Hence, Physics 973 Unit 3, Dynamics. Physics 974 Unit 3, Dynamics. Pressed against the rims provide friction. It is the friction that stops the bicycle. Wheel is one of the most important inventions in the history of mankind. The first thing about a wheel is that it rolls as it moves rather than to slide. This greatly reduces friction. Why? When the axle of a wheel is pushed, the force of friction between the wheel and the ground at the point of contact provides the reaction force. The reaction force acts at the contact points of the wheel in a direction opposite to the applied force. The wheel rolls without rupturing the cold welds. That is why the rolling friction is extremely small than sliding friction. The fact that rolling friction is less than sliding friction is applied in ball bearings or roller bearings to reduce losses due to friction. The wheel would not roll on pushing it if there would be no friction between the wheel and the ground. Thus, friction is desirable for wheels to roll over a surface. It is dangerous to drive on a wet road because the friction between the road and the tires is very small. This increases the chance of slipping the tires from the road. The threading on tires is designed to increase friction. Thus, threading improves road grip and make it safer to drive even on wet road. A cyclist applies brakes to stop his/her bicycle. As soon as brakes are applied, the wheels stop rolling and begin to slide over the road. Since sliding friction is force. Quick quiz 1. Which shoe offer less friction? 2. Which shoe is better for walking on dry track? 3. Which shoe is better for jogging? 4. Which sole will wear out early? Figure 3.18, friction may cause the body to roll. Figure 3.19, a ball bearing. Figure 3.20, threading on tires provides good road grip. Physics 975 Unit 3, Dynamics. Much greater than rolling friction. Therefore, the cycle stops very quickly. Braking and skidding. The wheels of a moving vehicle have two velocity components, I, motion of wheels along the road. 2. Rotation of wheels about their axis. To move a vehicle on the road as well as to stop a moving vehicle requires friction between its tires and the road. For example, if the road is slippery or the tires are worn out, then the tires, instead of rolling, slip over the road. The vehicle will not move if the wheels start slipping at the same point on the slippery road. Thus, for the wheels to roll, the force of friction, gripping force, between the tires and the road must be enough that prevents them from slipping. Similarly, to stop a car quickly, a large force of friction between the tires and the road is needed. But there is a limit to this force of friction that tires can provide. If the brakes are applied too strongly, the wheels of the car will lock up, stop turning, and the car will skid due to its large momentum. It will lose its directional control that may result in an accident. In order to reduce the chance of skidding, it is advisable not to apply brakes too hard that lock up their rolling motion, especially at high speeds. Moreover, it is unsafe to drive a vehicle with worn-out tires. Advantages and disadvantages of friction. Friction has the advantages as well as disadvantages. Friction is undesirable when moving at high speeds because it opposes the motion and thus. Figure 3.21, a car skidding. Quick quiz 1. Why is it easy to roll a cylindrical eraser on a paper sheet than to slide it? 2. Do we roll or slide the eraser to remove the pencil work from our notebook? Mini exercise 1. In which case do you need smaller force and why? I. Rolling. 2. Sliding. 2. In which case it is easy for the tire to roll over? I. Rough ground. 2. Smooth ground. Physics 976 Unit 3, Dynamics. Limits the speed of moving objects. Most of our useful energy is lost as heat and sound due to the friction between various moving parts of machines. In machines, friction also causes wear and tear of their moving parts. However, sometimes friction is most desirable. We cannot write if there would be no friction between paper and the pencil. Friction enables us to walk on the ground. We cannot run on a slippery ground. A slippery ground offers very little friction. Hence, anybody who tries to run on a slippery ground may meet an accident. Similarly, it is dangerous to apply brakes with full force to stop a fast-moving vehicle on a slippery road. Birds could not fly if there is no air resistance. The reaction of pushed air enables the birds to fly. Thus, in many situations, we need friction, while in other situations we need to reduce it as much as possible. Write a dream during which you are driving a car and suddenly the friction disappears. What happened next? Methods of reducing friction. The friction can be reduced by I. Making the sliding surfaces smooth. 2. Making the fast-moving objects a streamlined shape, fish shape, such as cars, aeroplanes, etc. This causes the smooth flow of air and thus minimizes air resistance at high speeds. 3. Lubricating the sliding surfaces. 4. Using ball bearings or roller bearings. Because the rolling friction is lesser than the sliding friction. 3.4 Uniform circular motion. We come across many things in our daily life that are moving along circular path. Take a small stone. Tie it at one end of a string and keep the other end of the string in your hand as shown in figure 3.24. Do you know? Friction is highly desirable when climbing up a hill. Figure 3.22, smooth airflow at high speeds reduces air resistance. Figure 3.23, streamlining the bullet train reduces air resistance at high speed. The Moon, the Earth. V. FCV. VFC FCV. FC. Physics 977 Unit 3, Dynamics. Figure 3.24, circular motion of a stone attached with a string. Figure 3.26, centripetal force is always directed towards the center and has no component in the direction of motion. Figure 3.27, A. A string provides necessary centripetal force. B. A string is unable to provide the required centripetal force. Now rotate the stone holding the string. The stone will move in a circular path. The motion of stone will be called a circular motion. Similarly, motion of the Moon around the Earth is circular motion. The motion of an object in a circular path is known as circular motion. Centripetal force. Consider a body tied at the end of a string moving with uniform speed in a circular path. A body has the tendency to move in a straight line due to inertia. Then why does the body move in a circle? The string to which the body is tied keeps it to move in a circle by pulling the body towards the center of the circle. The string pulls the body perpendicular to its motion as shown in figure 3.26. This pulling force continuously changes the direction of motion and remains towards the center of the circle. This center-seeking force is called the centripetal force. It keeps the body to move in a circle. Centripetal force always acts perpendicular to the motion of the body. Centripetal force is a force that keeps a body to move in a circle. Let us study the centripetal forces in the following examples. Figure 3.27 shows a stone tied to one end of a string rotating in a circle. The tension in the string provides the necessary centripetal force. It keeps the stone to remain in the circle. If the string is not strong enough to provide the necessary tension, it breaks and the stone. Figure 3.24, circular motion of a stone attached with a string. Centripetal force. Centrifugal force. Physics 978 Unit 3, Dynamics. Moves away along a tangent to the circle as shown in figure 3.27, b. 2. The Moon revolves around the Earth. The gravitational force of the Earth provides the necessary centripetal force. Let a body of mass m moves with uniform speed v in a circle of radius r. The acceleration produced by the c centripetal force F is given by c centripetal acceleration. According to Newton's second law of motion, the centripetal force F is given by c. Equation 3.26 shows that the centripetal force needed by a body moving in a circle depends on the mass m of the body, square of its velocity v, and reciprocal to the radius r of the circle. Centrifugal force. Consider a stone shown in figure 3.28 tied to a string moving in a circle. The necessary centripetal force acts on the stone through the string that keeps it to move in a circle. According to Newton's third law of motion, there exists a reaction to this centripetal force. Centripetal reaction that pulls the string outward is sometimes called the centrifugal force. Example 3.8. A stone of mass 100 g is attached to a string 1 m long. The stone is rotating in a circle with a speed of 15 milliseconds. Find the tension in the string. Solution. Figure 3.28, centripetal force acting on the stone and the centrifugal force acting on the string. Centripetal force. Inertia. Do you know? While the coaster cars move around the loop, the track provides centripetal force preventing them to move away from the circle. Physics 979 Unit 3, Dynamics. Thus, tension in the string will be equal to 2.5 N. Banking of the roads. When a car takes a turn, centripetal force is needed to keep it in its curved track. The friction between the tires and the road provides the necessary centripetal force. The car would skid if the force of friction between the tires and the road is not sufficient enough, particularly when the roads are wet. This problem is solved by banking of curved roads. Banking of a road means that the outer edge of the road is raised. Imagine a vehicle on a curved road such as shown in figure 3.29. Banking causes a component of vehicle's weight to provide the necessary centripetal force while taking a turn. Thus banking of roads prevents skidding of vehicle and thus makes the driving safe. Washing machine dryer. The dryer of a washing machine is basket spinners. They have a perforated wall having large numbers of fine holes in the cylindrical rotor as shown in figure 3.30. The lid of the cylindrical container is closed after putting wet clothes in it. When it spins at high speed, the water from wet clothes is forced out through these holes due to lack of centripetal force. Cream separator. Most modern plants use a separator to control the fat contents of various products. A separator is a high-speed spinner. It acts on the same principle of centrifuge machines. The bowl spins at very high tension T in the string provides the necessary centripetal force given by spinner. Spinner shaft. Figure 3.30, dryer of washing machines has perforated wall. R. W. A radius of the circular track. Figure 3.29, outer edge of the curved road is elevated to prevent skidding. Physics 980 Unit 3, Dynamics. Speed causing the heavier contents of milk to move outward in the bowl, pushing the lighter contents inward towards the spinning axis. Cream or butterfat is lighter than other components in milk. Therefore, skimmed milk, which is denser than cream, is collected at the outer wall of the bowl. The lighter part, cream, is pushed towards the center from where it is collected through a pipe. Figure 3.31, a cream separator. Summary. A force is a push or pull. It moves or tends to move, stops or tends to stop the motion of a body. Inertia of a body is its property due to which it resists any change in its state of rest or uniform motion in a straight line. Momentum of a body is the quantity of motion possessed by the body. Momentum of a body is equal to the product of its mass and velocity. The force that opposes the motion of a body is called friction. Newton's first law of motion states that a body continues its state of rest or of uniform motion in a straight line provided no net force acts on it. Newton's second law of motion states that when a net force acts on a body, it produces acceleration in the body in the direction of the net force. The magnitude of this acceleration is directly proportional to the net force acting on it and inversely proportional to its mass. Mathematically, F equals ma. SI unit of force is Newton, N. It is defined as the force which produces an acceleration of 1 millisecond in a body of mass 1 kilogram. Mass of a body is the quantity of matter possessed by it. It is a scalar quantity. SI unit of mass is kilogram. Weight of a body is the force of gravity acting on it. It is a vector quantity. SI unit of weight is Newton, N. Newton's third law of motion states that to every action there is always an equal and opposite reaction. The acceleration and tension in a system of two bodies attached to the ends of a string that passes over a frictionless pulley such that both move vertically are given by. The acceleration and tension in a system of two bodies attached to the ends of a string that passes over a frictionless pulley such that one moves vertically and the other. Physics 981 Unit 3, Dynamics. Moves on a smooth horizontal surface are given by. Law of conservation of momentum states that the momentum of an isolated system of two or more than two interacting bodies remains constant. A force between the sliding objects which opposes the relative motion between them is called friction. Rolling friction is the force of friction between a rolling body and a surface over which it rolls. Rolling friction is lesser than the sliding friction. The friction causes loss of energy in machines and much work has to be done in overcoming it. Moreover, friction leads to much wear and tear on the moving parts of the machine. The friction can be reduced by I. Smoothing the sliding surfaces in contact. 2. Using lubricants between sliding surfaces. 3. Using ball bearings or roller bearings. The motion of a body moving along a circular path is called circular motion. The force which keeps the body to move in a circular path is called the centripetal force and is given. According to Newton's third law of motion, there exists a reaction to the centripetal force. Centripetal reaction that pulls the string outward is sometimes called the centrifugal force. Questions. Point 1. Encircle the correct answer.